Should comment on the first
Take it over to
Alright. Hey. Okay.
Almost killed a couple people.
Hi.
Alright. Today.
Anyway.
Alright.
Did you give up on your phone? Did you give up recording?
No, we're gonna talk about it right now. Alright. On Monday, I recorded in 4K. I'm going to continue to do that starting tomorrow. In fact, this camera, we won't be using this one anymore because I had confirmation from another class that the 4K video that I recorded from Monday's class, just as a trial, it actually does output in 4K. You have to have a 4K capable computer.
Chrome pads though.
Yeah, Chrome pads. My MacBook doesn't. My iPads used to, but Google changed their policy. It has to be a 4K resolution screen. So. I know if you have like a Samsung phone, they can actually have 4K for a screen. They can go up to 1440, which isn't 4K, but it's close. So it was confirmed they did actually watch the video in 4K of their class. So it is there, but you have to have a capable computer. Now I know that's silly because pretty much no one has them. But what that tells me though is that if somebody were to get a computer that was capable, or a phone or a tablet eventually, because they will be upgraded eventually, that it is playable. Now what it just does for everybody else is just downscales to 1080p. You're normal, you wouldn't notice any difference. So from now on I will be using my phone to record classes strictly until I get my new camera that's 4K capable. The only thing I'll need to make sure of is that if the audio quality fails, like it's poor compared to this one, because this one has a nice microphone, I'll make sure that we have a solution for that. I'll see if I can connect the microphone to it. Because I have a couple dongles that will actually hopefully make it work. So we'll try that. If the audio is poor. From the video that I recorded yesterday, the audio was just as good as using this one with a microphone. So the iPhone's microphone is actually really stellar. Until my new camera comes in, I'll just plug in that microphone.
You know what we should do? I got us more iron.
Okay.
We should just get better computers.
Question.
What student had the 4K capability that took your work?
That was Stephen Phillips. He had a gaming computer.
Yeah, that sounds about right. He probably has one.
So, he said it looked really good. The quality was just, you could tell it was instantly better just looking at that versus the other. So I'll do that from now on. Only certain kids have the capability. I know no one in the right mind to use it, but
Not sure for the stuff with text, that's what he was doing.
no, most graphics cards can output in 4K. It's just that their resolution for the monitor is what you kind of require.
And I tell people I have to call
That
it
might be expensive.
the night. And like, oh, here's the test. All the
$200 for the
looked at it,
monitor.
write everything down.
That's expensive.
Our Chrome pads don't differentiate the graphics cards.
What? $200 to $300 for probably a 4K monitor. For
Why are they going to
so that's about normal. Nicer ones depends on the quality of it, the size. Yeah. So I just have my. That's all I have. All right. Now, hey, real quick, you need your project out in front of you. We're going to talk about it. We're going to finish this up today.
You didn't ask me about it.
Mr. Ward, can we know
What class? I think they watched that same one. I have Scooby-Doo Bandits, don't they?
Is that statistics?
Sid, Jason, here you go.
How do you say?
And Dalton.
They're pretty cool.
Mr. Warner, we're getting notes today too.
Yeah, we're getting notes.
No, we're not.
We're taking.
He's just kidding.
That's what I was thinking.
Okay, I'm going to wait you guys down so you guys can remain quiet. Because you're getting homework today no matter what, and it's due on Friday. So,
No matter what.
now,
Sure, do you like any shots?
so, all right, on your project, the one thing we're going to have to do, you have to write down your information in 3 different forms. Yesterday we didn't really get to this, it was right at the end of class when I was asking you to do this. So, let's say that your information looked like this. I have no idea what yours kind of look like, but let's say this is kind of what your numbers look like. So it kind of mimicked this. Some people's didn't, depending on the actual tennis ball that I gave you. But some data look like that. Some people's, it was going up, like, let's say this is the X and Y axis. Some of their data was going like this. That was some tennis balls was doing that. There was a couple in here that it was the same bounces no matter what height they dropped.
That'd be awesome.
Okay, it happens. It just depends on the tennis ball, the quality of it. It was kind of all over the place, so everyone kind of had a different setup to it. but I do want an equation that would represent your line. So what you had to do, you had to find the best fit line that goes through it. Shh. So the best fit line that went through it. Okay, stop talking, seriously. So, best fit line, you have to find the slope by doing this. Okay, Reese, sit here. You can't stop talking. So y minus y, x minus x, you have to find slope. Once you have that slope number, then you have to put it into point slope form. Now, what I mean by point slope form, you had to pick one of your coordinates from your graph that was on that line, this line, the best fit line, one of the coordinates that was on it, and then you had to use the slope that you just found, and that would be your equation. You can rearrange this one into the other forms. Because let's say your numbers were, it was going up 1 over 4. Let's just say that was your slope. I have no idea what your slope was. And one of the coordinates was, that you had picked was maybe 2, or it was 5 comma 8. Let's say that that was one of your coordinates. You had, from 5 feet, it bounced 8 times before it stopped. So that would be a 5 and an 8 here. You would distribute the 1/4 through, like this. And when you distribute a 1/4 to the 5, it'd be a 5/4, because you actually take the 5 times the top. And to get to slope-intercept form, you would add the 8 across. And you have to add an 8 to 5 and 1/4. 5 and 1/4 is 1 1/4, by the way. If you want to simplify that, it's 1 1/4 or 1.25. You can add the 8 across, and combine that would be your slope-intercept form. Now, the reason why we did this, the whole point of this exercise, other than collecting data, and actually coming up with an equation for it, was that you need to see what the potential is, and that's what that secondary page was. So on the back where it says Algebra 1 at the top of the worksheet that I provided you guys, you can actually use this equation to predict what will happen at 50 feet down the road. Okay, 50 feet. If you had your formula, this one, 1/4, and that was going to be 6 3/4. If I were to add the 8 across. If that was your formula, oh, forgot next. You can actually predict what will happen at 50 feet, because the x's represent what feet you drop it from. And all you have to do is plug in the 50 into one of your formulas, one of the 3, because you had 3 different versions. And the 50 went to the x location. This will tell you roughly how many bounces it should take. It's not super accurate. You'll see that because it depends on the ball itself. It depends on the actual conditions that you're dropping it in, how many bounces it will take. But that's what we use this stuff for. Now, what we're in today, what we're in this chapter is all about slope and rate of change and first derivatives. First derivative is actually looking at the slope only. You can actually use that, if you actually had a first derivative, you can actually use that as your slope number. It would be actually more accurate if you did it. Now, the only problem is, on these curves, some of you had curves, some of you didn't, on these curves, the slope changes. So it's actually important that if we're going to these equations, that this is actually what you have. And whatever the y-intercept is. In most people's cases, the y-intercept should be 0. You should hit 0 if you were hitting the y-axis anywhere, because you didn't have, if you dropped from a height to 0, it would stop bouncing instantly. Right? So, now why I wrote it like this? What does this thing mean? What does it mean when I have a little, like,
F prime.
It's f prime, it's a derivative. Ooh. If you actually found the derivative, if you actually knew your formula, and you found a derivative, and we had an equation for this type of system, and you actually found the derivative using that limit formula, limit as h approaches 0 for all that, f of x plus h, and you subtract. If you actually plug that in here, that crazy limit, and you had an ever-changing derivative, a slope, f prime, whatever you want to call it, you would actually be able to figure out the potential of where you're going to go at any moment. So at any moment down the road, the slope might be different. Well, that would give you a different predictor at 50 feet down the road. For the closer to 50 feet you get, the better that prediction is. There's one probably case in here, and I think it was the 2 ladies here, their number was flat. It didn't matter what height they dropped their ball from, it was giving them the same number every single time. Because the ball was totally broken. It was crushed. So, usually, what we want to see is probably that top one, that top right box. A lot of people think it's this one.
Kind of like ours.
It's not. It's actually this. There's actually a limit to how many bounces it can take because of gravity and the weight of the ball. I think in previous years when I've done this for a long time ago when I was in Cal, I think the limit was like 12 to 14 bounces. Like that's a limit. Even at 50 feet, it only bounced about 12 times.
How often did you drop it from 50 feet?
We in Ventura we actually had a press box that we dropped it from in the gym. And it was almost exactly 50 feet. It was like 49 and a half feet. So we dropped it. It took about 12 bounces, and they were like, all their numbers were predicting like 60 bounces ish. It was like stupid numbers, but it was 12, and they couldn't figure out why, because they were all looking at the lines, right? They were looking at the predictor, the best fit line that was like pointing that a direction, but they don't realize it's curving. Like gravity's going to eventually take over. There's a limit to the fall, the velocity of it, and so there's only a limit to the distance you can fall, or the velocity that you're having. So it'll eventually stop. It's kind of crazy when you see it because that first drop is really big, and the second bounce only goes a little bit up in the air, and basically resembles everything you did yesterday. Like when you dropped it from 10 feet, that reaction that the ball had is almost exactly at 50 feet. It goes up about the same height, and then just levels out again.
I think we can test this. We should go to the odd and you drop it from the sound booth.
Oh, yeah. I mean that would work
We need to do that.
if you had like a perfect 50-foot
We already
drop
do
and
that.
everything. Yeah. I think the only problem is in that odd. I think the stage kind of slopes a little bit. You won't get a great bounce on it.
Oh, we could miss your work. No, guys.
All right, now hey, what I'd like to do today, if you haven't already, and I'll give you time at the very end of class day. I need you to come up with your 3 different equations, plug in your 50 into them, or at least one of them, to predict what will happen. Some of them are easier than others, but I need those turned in today, and I want you to see the difference between what we've learned versus what we're going towards. Okay, you can put the little project off to the side for now. You just need your notes out for right now. I'm going to go about 5 or 6 minutes into notes, and then I'm going to give you time to work on your homework today, and you'll have plenty of time today to actually work. Okay? All right, here we go. So I'll give you some time today at the very end of class. You can kind of finish up that little project that we're doing. I want you to see the difference between average slope and derivatives change over time, and that would change your predictor. That's what I want you to see. All right. Let's get rid of this for right now. All right. All right, so first, the first problem that's going to be in your homework today, they're going to give you functions, something like that looks like this, and they're going to say they want to find 2 different things. They want to find what would happen at f of 4 and what is f prime of 4.
Is this an exact total problem?
Okay, yeah, I mean these look. This one looks nearly identical to that first problem you're going to see.
So the first one was?
Yeah. Now, here's the idea. You have to do 2 things. Number 1, you have to understand what the differences are here. The first part here is just evaluating the function at a number. You can plug the 4 in and see what it gives you. So if I were to go f of 4, that means you're going 2 times 4 plus 3 times 4 squared. Right? That's all that top one is. It's you're evaluating a function at a certain number. F prime of 4, or f, the first derivative of f evaluated at 4, is different. That's where you have to do this.
X plus h.
Yeah, where you go f of x plus h minus f of x all over h. You plug in your function in here. My function is this thing. So I have to plug in a bunch of x plus h's. Limit as h approaches 0. And I'm going to have in the first box 2 times x plus h plus 3x plus h squared. Subtract the original problem. All over h. So you're doing that differential quotient. When you simplify this thing down, you've evaluated, you've simplified, and it turned out to be something like this. 2x plus 2h plus 3x squared plus 6xh's plus 3h squares minus 2x minus 3x squared.
Something like that, or exactly that.
All over h. Okay.
That was exactly the answer.
Yeah, and the idea is that once you have that and you divide everything by h, so you simplify like these are gone,
It's been a cancel.
these are gone, the h's will all divide, and then whatever is left, you still have to evaluate it at 0, because h is approaching 0 eventually, but I need to divide these out, so I'm gonna have the limit as h approaches 0 of 2h plus 6x plus 3h. That's dividing everything by
I just
h.
want to say that you're going very fast.
No, it would
Yeah.
just be 2.
Yeah.
Oh, 2, thanks.
Yeah.
Yeah. All right.
I said
So-
you're going very fast.
Yeah.
So I divided everything by h, and now I'm going to plug in 0 for all the h's. So I'm going to have this left over when I actually evaluate. What this represents, this
Plug
thing,
in the 4.
yeah, that thing is your first derivative. You then would plug in the 4 because that's the formula for the first derivative. That's the slope at any point on this curve. So this,
I kinda like derivatives.
it would be this. This is what we're looking at. And you have to plug in the 4 into that first derivative. That's the thing we simplified to. Now the reason why I want you doing this, the book did not ask you to do this. The book says, and I don't like the way they do this. They say they want you to make a table, plug in a bunch of numbers that are around the number 4 for the first derivative. You plug them in, and you see, and you find. And here's the worst part: you have that table with all the numbers that are really close to 4. Then you find the slope between a bunch of them that are really close together, and then yeah, then they say your slope is roughly that slope that's in between the ones that are really close to 4.
Give us the exact answer.
This is the exact answer.
Right, but the book doesn't want us to.
No, it wants you to do this crazy work that would take 90
Hours.
times longer than what I'm doing here.
They don't want us to succeed.
So question,
Yes.
what is the answer to then f of 4? Is it the 2 plus 6x that you
The
found?
f prime of 4 is
No, the top
this
one.
thing. Oh, the top one. That would be 8 plus 48. So 8 plus 48, what is that?
56.
56?
I love how you can do 4 squared times 3 and then you're like, 48 plus 8.
I can't add in my head. I can multiply and divide. It's stupid. I can't explain it.
You can square.
I just don't.
Okay. Now,
Don't care about
now, the next part. Now the next part. They're going to give you a picture. So we're going to go back to this graph over here.
Literally this part taken over that.
Okay, they're going to go back to a graph, and they're going to do something like this. And they're going to have this line. This is the tangent line. It's perfectly tangent, so that's your slope. They're going to say that this coordinate, and again, I can get rid of this graph. They're going to say that they're going to give you that f of 3 is 3.
For f, the f prime 4 thing.
Okay, they're going to give you something like this, and what they're going to ask you to find is what is the coordinates at f
Yeah.
on f prime of like 5.
Oh, crazy.
Okay, they're going to ask for that.
Three f
And the idea is that what they have is they have these dots that are somewhere down the road, and they want to know what is the coordinate that is here and here, because this one might represent your 3, 3.
Would you plug a 5 into
Okay.
that then derivative?
So, we won't have to find the derivative. If you find the slope of this line, because they're going to give you some numbers you can actually find slope, right? You can use the slope, and that will help you to set up this equation that I was showing you earlier. That if you know where this line goes through,
Right, that's what you have.
like you understand this y-intercept, you can plug in the slope. I think they even give you slope at some point. You have the slope, that's the number in front of x. You have the y-intercept. You can predict where that dot will be if you just know the x number on it. Because you'll have to, because they'll give you the f prime number. They'll say maybe your slope is 3/2, and maybe you're going through 0, 0. All you have to do is plug in 5 into that equation, but this is the part you had to plug in. You had to plug in the slope there. The slope is the first derivative.
So what's the second derivative?
Second derivative is acceleration. So when you draw these lines, when you draw curves, and how steep they are, there's an actual flow to it. So the steeper they are, the slower the dot goes. And then when it turns directions and goes steep, it goes really fast like a roller coaster. And you actually see it in real time, like how it goes above a graph and how it drops and stuff. And what a second derivative tells you is what's the speed at that exact moment? How fast is it going? So by knowing the second derivative, you can tell if you're going uphill or downhill.
Is that harder to calculate?
No, it's just another derivative.
Is it the same formula?
Same formula. You're just you're taking this
plugging
and doing
it
it
into
one
there?
more time.
Do you plug the average?
Yeah, you're plugging this into that thing again.
You do that right now.
Wait, does he get a lot bigger then?
No, they get smaller and smaller and smaller as you go.
I mean,
Like I'm predicting the answer for the second derivative on that problem will be 6. That's what I'm predicting,
You're
and I'll have a bunch
predicting
of
what
answers.
is that?
It's 6.
There you go.
How do you know?
I've taken enough calc in my life, I know the answers immediately when I see the
It's
problem.
6.
You're like a cheat code for math.
So, like when I saw that problem earlier, I knew it was gonna be 2 plus 6x.
X squared plus 6x.
How do you know it's gonna be plus success?
What?
How do you know it's gonna be
It's
plus
6.
success?
There's shortcuts you're eventually gonna learn here. I'm gonna teach you the
Why
shortcuts.
would you just teach shortcuts right away?
What, you gotta appreciate the real math.
I don't appreciate it.
I'm never gonna
I'm
appreciate
predicting
it.
Okay.
that will be 6.
Hey.
Word, I love your confidence.
Yeah, it's 6.
What?
So I love your confidence there.
Alright,
Yeah.
here we go.
Yeah.
49.
Okay, page 87, 1 through 3, 6, 10 through 13, 17, 18, 22, 23, and 25.
I've got 26.
It's like
On
learning how to
James,
jump
it's
before you
26.
can walk.
Don't say that, why would you say that?
Yeah, why would you actually say that though?
I don't have it on James yet.
Jamesy.
So,
And James.
I was gonna, I haven't posted it yet. It goes up tomorrow. Okay, alright, there's your homework. It's based on first derivatives that you're doing here. It's based on finding lines itself, looking at a graph and telling like what the slope is at a graph, just estimating like, okay, that graph looks like the slope is about 2/1, it's positive, and I just made up a number there. You're just doing a lot of simple things, but it's getting you used to the definition of what derivatives mean versus a graph versus an equation. The book is gonna ask you to do stupid things. You can calculate first derivatives,
I'm not gonna do it.
do first derivatives, plug in numbers,
Either way.
or you can predict other numbers by using the simple linear equation. That's why we are doing this whole project.
I have a quick
You need to take the next 10 minutes or so, because then we have about 10-15 minutes left of class. You need to finish up your project today by graphing it and figuring out your equations and predict what will happen at 50 feet.
Quick question.
Mr. Wood.
How do you figure out?
The interweb will tell me. Two little,
Can
it's
I
like
raise my
a.
hand? I'm not doing it.
Deal. Can you,
Wait, so we're just doing a line that
Justin, can you do
approximates
your
each point, like a straight line through all the points?
Yeah.
Sit down and be
Alright.
humble.
Don't
Yeah.
throw that. Mr. Ward, question. What's the third derivative for that problem?
Third derivative, 0.
Okay, but what is the third derivative? What does the third derivative mean?
Yeah, so the one's a loss.
It would be the acceleration of acceleration.
At what point in time do they lose their relevance?
Wait, did you say,
After usually second derivative,
It's just like-
Hey, if they're all
Second
in
derivative is like
between,
an average
so
of an
it's gonna go
Yes,
through right
it's an
here.
average.
It's the acceleration of the
With our,
acceleration.
with our.
Go to the balance sheet.
acceleration.
Acceleration.
I don't get how much
Should we just mark here and then go?
What?
Should we go here?
1.75, go with what the predictor line is. The predictor line is gonna
Hey.
go
Yeah,
up.
well,
What?
slow.
So where's the straight line between the two? 1, 8, 10, 8?
Say it again?
What are our points?
Okay, so your straight line, so the equation for that line,
We're doing this one at
y equals the number, because you don't have an x, because it's not slanted. So it's just straight. So y equals, and then what number did you pass through?
That's the.
Actually, there's a little
That's the
tilt.
Only this one.
Oh.
Just only that one.
Okay, perfect, so use that as your slope then. So the difference between these two,
The other 13
so use those two to find, yeah, you can.
8.3 and 8.5.
Boom, you got it. So find the
Does this look like a
differences.
standard form to you? Does this look like a standard form to you?
Oh, there has to be.
Standard form, yeah, what's up with what's that thing?
Mr. Ward, what's the hardest math project that you have to complete?
Y plus 6x plus a number equals, yeah, that's technically, that's technically, or standard form would be having the number on the other side of 0. Is that supposed to be it?
I don't know.
That would be standard.
Doesn't matter.
You take it off?
So it's just fun.
I'm just having.
0.2 over 1.
Why?
Now I'm making stabs.
What
There are some
class?
problems where there were more every aspect.
It's your slower.
Don't break it.
For this method,
Do that.
for the middle part.
Well,
You
what's-
have to prove, approve, and approve, you know what I mean? Like when you use like a different theorem, it all different forms.
But what problem was it? What were you doing?
You want us to do the job, so.
Mr. Ward, what was the problem
Would
about?
it be f of x?
Just plug 50 in there, and I'm done.
First job is 1 here, then find 1 here.
Word.
So we want to use this.
Word.
I know a note.
I'd have to look.
You know this, come on.
Yeah.
I remember doing it and it took multiple pages of
But how much time?
This is a.
Like hours?
yeah, like multiple days in the week, but not like full days, but like working on
Like 10 hours plus?
probably.
Pat, Mr. Ward just told me that he wants to do the math problem that took over 10 hours.
Super science.
Did you plug
It was a
in?
multiple page proof.
Turn off the camera.
Super sane.
Yeah.
Do we have to do it for both of the graphs?
Yes, you have to plug
Are
in.
you kidding me?
I don't know.